Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 4.3, day 2, entitled Logarithmic Functions. And today we're going to talk about common logs and natural logs. Now the common logarithm is when you have a log with a base of 10. And usually we just call that log of x. So if there is no base written in, you can assume that there's a little 10 there. So log base 10 of x. So usually they just write it this way, log of 10. And again, there's that little base 10 written in there. So 10 to the first power would be 10. And here, log base 10 of 100, 10 to the second power is 100. So that circle method that we talked about in 4.3 day 1 still applies here. Now there's a question here at the bottom that says, how would we find log of 50? Okay, so if we put the little 10 in there for the base and set it equal to x, we'd have log base 10 of 50 equals something if we're trying to evaluate it. So you'd have 10 to some power equals 50. That's what they have written here. 10 to some power equals 50. Well, 10 to the second power is 100, and 10 to the first power is 10. So you know it has to be a number between 1 and 2. So log base 50, whatever that is, or log of 50, has to be between 1 and 2. And if you wanted to find an exact approximation of that, you'd have to do it on your calculator. And you can just type in log of 50, and on your calculator, if you do log of 50, it should give you about 1.69897. Usually we round logs to 4 places when we're writing their decimal. I have 5 there, okay, but at least 4. So if you were to see that type of a problem in homework or on quizzes or tests where it says to explain or evaluate it without using a calculator, that's what we're looking for, okay? So you'd need to say 10 to the first power is 10 and 10 to the second power is 100. So I know that if I want 10 to some power to be equal to 50, it would have to be between 1 and 2. Okay, so let's look at this example here where they want us to graph log of x. And again, this is log base 10 of x. It's our common log. Now, like we saw in the previous day's notes in 4.3 day 1, we're not going to necessarily start with the x values in our table of values. Now we could make a table of values where we find or pick some x values and plug them in. Now, I want to point out here that there are certain values for x that we can't put into our function. We noticed it yesterday when we talked about our vertical asymptotes, but I didn't explicitly point it out. So hopefully by now you're noticing that our domain has to be all the x's greater than 0. Not even greater than or equal to. So if I am going to pick numbers for x and evaluate log of that number, I can't pick a negative number because I'll get an error. I can't pick 0 either because I'll get an error. But I could pick fractions, like 0.5, fractions are decimals. I could pick whole numbers. Okay? But if you're going to pick a number for x and put it into a logarithmic function, it has to be greater than 0. Okay? And that's because you can't take a number to some power and get 0 as an answer. So if you want x to be 0, that would say log base 10 of 0 is to equal something. So you would need 10 to some power to equal 0. You can't take 10 to any power and get 0. That's why that's undefined. Okay? So you can make your table of values this way, and we'll get negative 0.301, 0, 0.47, 1. Okay, so you can make a table of values that way. But if you're trying to make your table of values starting with your y values, okay, that means you would want to fill in this column first. So let's just say we had, if we were thinking of this in kind of like a circle method, like I wrote over here, we would have 10 to some power equals x. Okay, so you have 10 to the y equals x. So these are the values that I would pick for y, like 10 squared, 10 to the first, 10 to the 0, 10 to the negative 1, negative 2. Okay, so then this number, the 2, would get substituted in there to the exponent. So 10 squared, that's going to be 100. So if I take log of 100, I'll get 2. Or if I had 10 to the first power, that's 10. So if I took log of 10, I'd get 1. Um, 10 to the 0 is going to be 1. 10 to the negative 1, that would be 1 over 10, or 0.1. 10 to the negative 2, that's going to be 1 over 100, or 0.01. So doing your table of values this way, where you're choosing your y values first and then getting the x values, can sometimes go a little bit easier. When you graph them, though, for this problem, regardless of what you select, if you're selecting your x values or your y values first, when you make your table of values, you're going to get the same shape in your graph, as these points are still on this graph. Okay. So let's see, we'd have 102, that's going to be way off my graph. 10, 1, 1, 2, 3, 4, 5, 6. Okay, that is 10. 10, 1, and then 1, 0, and then 0.1, negative 1, and then 0.01, negative 2 be way down here. So my graph is going to go rather gradually to the right. So even if I plotted these values over here from this first table where I chose the x values, okay, 1/2 negative 3 might be right in there. 0, 1 is still on there. 1, 2, 3, and then a half. Kind of looks like I went through that. Okay. So here's the nice, neat book graph. So it's a little bit neater. Okay. And it looks like they might have picked x values first and plugged them in and evaluated them because they are getting some elaborate decimals here. But remember that characteristic from yesterday where we talked about starting with the y values in your table of values, because that can be easier. Now, logarithms do have applications, okay? And this application talks about how scientists can model human responses to stimuli using logarithmic functions. And there's an equation here for the intensity of sound. So the intensity of sound must be increased many-fold before we actually feel the loudness. And psychologist Gustav Fechner formulated this law. Okay, so this is a good application for logarithms. And notice that it's log base 10. It's just log. Okay, and it says S is the intensity. I is the physical intensity. I sub 0 is the threshold of physical intensity, and K is the constant. So in example 8 here, we're going to apply that. We're going to find the decibel level, or the soundness, or the loudness, sorry. So B is the loudness, so that's what we're going to be finding, of a sound whose physical intensity I is 100 times that of I sub 0. Okay? So if I has to be 100 times bigger, we could just make 10 log, and if you want to put the little log base 10 in there, you can. We could just make I 100 and then I sub 0 1 if it says it has to be 100 times that of I sub 0. Or we could make I sub 0 5 and make this 500. Okay? So basically now you have 10 times log base 10 of 100. Now this we've already evaluated. This we've done a couple times on the previous slides. Okay? If we took this expression, log base 10 of 10, and set it equal to x, and did our little circle method, we would have 10 to some power equals 100. Okay? So that means that something has to be 2. So if you did log of 100 in your calculator, you would get 2. So that's really 10 times 2, which is 20. So 20 is going to be our answer there. 20 is the decibels, I guess we could label it. 20 decibels that a physical sound would have to have in order for it to feel 100 times more intense. Okay? So remember those properties for simplifying logarithms, even when you see them in more complicated applications. Okay, now we're also going to talk about natural logarithms. And natural logs are when you have a log base e. Remember, e is just a number, and it's 2.718281828. It's just a number, but it's a very special number in calculus. It helps us evaluate things constantly every second. Okay? So when you have a log base e, we're going to rewrite it as natural log. And remember that the natural log is the inverse of e to the x. And since they're inverses, here you have e to the x that's graphed. Here you have your natural log of x that's graphed. And again, they reflect over this line y equals x, just like logarithms and exponential functions did. Okay, e to the x, that's still an exponential function. Natural log of x, that's still a logarithmic function. They're still inverses. They're still going to have all those characteristics that we talked about in the previous section of notes. And they're still going to follow those properties for logarithms that we saw. So 3 and 4, property 3 and 4 here, that says when you have a natural log of e to the x, this is basically log base e of e to the x. So when we have the base on the log and the base on the power that are the same, they cancel. And you just get x. Same thing when you have e to the natural log of x. That's like e to the log base e of x. So again, your base on your logarithm and your base on your power are the same, so they cancel. And for property number 1, again, this is like log base e of 1 equals 0. So e to the 0 power is 1. And here, the property number 2, that would be log base e of e equals 1. Okay, again, that you could think of it as canceling or thinking of it as e to the first power is e. So those properties that we talked about in section 4.3 day 1 still apply to the natural log. Okay, so we're going to use those properties. Now we're just working with natural logs instead of logarithms. So the natural log of e to the 8 equals x. So there's a couple ways that you could approach this. Okay, we want to set it equal to something. And then remember, this natural log is the same as log base e. So you could think of it as log base e of e to the 8 equals x. And then here, when the base on the logarithm and the base on the power are the same, They just cancel. So 8 is equal to x. If you wanted to think of it like a little circle method, you could. You could do that too. You'd have log base e of e to the 8. So you'd have e to the x equals e to the 8. E to the x equals e to the 8. And then the bases are the same. So x equals 8. So there's a couple different ways that you can think through that property. Or you could just think, hey, when I take the natural log of e, that cancels. So x has to equal 8. So there's 3 different ways to look at part A, and they're all correct. Now part B, I want to rewrite that just a little bit because I don't like 1 over e squared. That can look a little intimidating. So let's rewrite that as the natural log of e to the negative 2. Because that's really what that means. If we had a negative exponent, it would move e to the second down to the denominator. So now to move it up to the numerator, I'm just going to make the 2 a negative. And again, the 3 ways that we looked at problem number 9a would still apply here. This natural log of e, they would cancel each other out. And then you just get negative 2 for your answer. Or you could think of it as log base e of e to the negative 2, and they cancel, and you get the negative 2. Or you could think of it like the little circle method where you set it equal to x, and e to the x equals e to the negative 2. And the e in the bases cancel, so x is negative 2. Now part C, there's really no algebraic way to do this. This you just have to do on your calculator, okay? This one you would just have to take the natural log of 5 on your calculator and then round it. And you want to round it to about 4 decimal places. And you should get 1.6094. Okay? So remember, when you're dealing with logarithms, round them to at least 4 decimal places. Okay, last example is the domain of logarithmic functions. I mentioned this when we were dealing with the graph back in example 7. And for our domain for logarithmic functions, remember we can't take the log of 0 and we can't take the log of a negative number because you can't take a number to some power and get 0. Okay? You can't take a number to some power and get a negative number. So we have to have a domain that's going to be greater than 0. So that means I want, if I'm trying to find the domain of this function, natural log of 4 minus x squared, that stuff right there is what has to be greater than or equal to 0. Whatever I take the log or natural log of has to be greater than 0. So I need to take 4 minus x squared and set it greater than 0. And then just solve for x. So I can subtract the 4 over. And when I divide by the negative 1, remember that's going to flip my inequality sign. And then I'm going to take the square root. Now, when we're taking square roots here with inequalities, temporarily I'm just going to think of it as an equation just for a moment, because when I take the square root of 4, I get 2 and negative 2. But to think of this as an inequality, I need to put negative 2 and 2 on my number line. Now this inequality was a less than, so a less than's an and. So I would have an open circle on both of those, and I would shade in the middle. Now if you didn't remember that, you could test a couple points. Try plugging in 0. Okay, if I had 0 squared, that would still be less than 4. Okay, so this is where I would want to shade in between, because that value that I substituted in gave me a true statement. So that means my domain has to be all of the x's such that negative 2 is less than x is less than 2. So I need to be between -2 and 2. You could write it in your interval notation too, like that. Either one would be correct. So again, this is just emphasizing that we can't take the log of a negative number and we can't take the log of 0. Same thing for natural logs. Natural logs are still logs, they're just log base e. So you can't take natural log of 0, can't take the natural log of a negative number. So that's why our domain has to be greater than 0. Okay, so here is your set of practice problems for this section. Make sure that you show your work. If you're doing a graph, make sure you write down the table of values. And if you have questions, come on in and see me before school.